right, we're on to the next session here. Looks like it's RADOS metadata-only journal mode. Lee, if you'd like to give us an introduction, we'll go from there.
Okay. So please refer to the blueprint. It's a detailed description of our idea. So currently, the Ceph community is thinking of eliminating the double write penalty of write-ahead routing. So while new store is a great design, which implements great and append operations in a copy and read way, while keeping all the original Ceph schematics. So this makes the new store a general purpose optimization. So especially suitable for those like write once scenarios. For our metadata-only journal model, we intend to do in a more aggressive way. That is, we don't journal object data at all. So we think this, of course, not a general purpose optimization, but this applies at least two major kinds of situations. The one is the scenario like for RBDE to simulate a disk in cloud platform. In that case, so we don't need the atomicity for object data modification, since for the disk semantics, for the block device semantics, so it's happy with either old or new content on an interrupt write. So we don't need to maintain the optimicity. And another use case is those double generating situations. For example, in cache tiering. While cache pool has already provided the durability. So when dirty objects are flashed back into the base pool, they theoretically need not go through the generating of the base pool, since the flash could always replace the write operation. Another situation is like the multiple object transaction support. We will talk to it later. So in that case, we can also skip the double generating penalty. So for those cases, the metadata-only journal mode to some extent resembles the data equal to ordered journal mode in ext4. So with such journal mode is on, object data are written directly to their ultimate location. When data written finished, metadata are written into the journal as usual. So it's actually guarantees the consistency in terms of the RADOS namespace and the data consistency among all the object copies. Just in some very rare cases, the object data may not be correct. In terms of correct, we think there may some old data fixed with some new data. Okay, so this is the motivation. So for implementation, we have two algorithms. We have two options. So for the first option, so it makes the minimal revision to the current front work. So just we divide the current implementation of the write operation into 3 steps. Now it's like 2 steps. We add 1 step. So we write the object data first, directed to the ultimate location. So for the second step, we commit the metadata to journal as usual. And after this, when we collect all ACKs from the slaves, so when the master told the slave to submit the metadata, that is apply the metadata to their ultimate location. So only one step is added. So this enjoys the simplicity of implementation. So we think in most cases this will not introduce a problem, since we have for Ceph we have the powerful peering and the client retransmit the mechanism. So for this implementation, the only problematic situation is if PG done, the whole PG is done, and the client also done. Since if it's not that case, if just one OSD in the PG survived, it can instruct other PGs, other down PGs, other OSDs in this PG to recover to a consistent state and a correct state. So the only situation is that if the whole PG is done, and the client also done. In that case, we can still expect the guessFS, the guess file system in the virtual machine. And when we do a guessFS remount, it will possibly recover it to consistent by FSCK and journal replaying. Like when a virtual machine is done, when we restart the virtual machine, we normally do FSCK, and also the guessFS will do journal replaying. It's hopefully also can recover the state consistent. So we think the problem situation is really rarely happen, and in that case, if that does happens, so we just leave the scrub to find and fix this by randomly synchronizing one of the copies to the others. So far, any questions?
Oh, yeah.
Yeah. So shall I continue for the second algorithm, or?
Yes. Go ahead.
Okay. So for the second algorithm, so we can do it more elegant, and we can like exactly resembles the semantics of block device. That is for the second algorithm, we do it in 4 steps. So for the first step, we commit transaction A into the journal. For this transaction, we add an unstable flag in the object metadata, as well as a PG log record. So this record will update the PG log version by 1. And then for the second step, we write data to object. So for the third step, we commit the transaction B into the journal and to do the metadata update as usual. And they also, in this step, we will revert the operation of transaction A. That is, we will delete the flag from the object metadata. And it will add another PG log record and update the PG log version by 1. That is for a traditional case, a transaction will only update the PG log version by 1, right? For now, we will update it twice. And for the last step, we just apply the metadata. So for this algorithm, as long as one OSD in the PG has succeeded, the PG will be recovered to a consistent and correct state by the powerful period. So if the PG done as a whole, there are the following situations. So there are basically 3 situations. The first situation, none of the OSDs finished step 1. And that is to say low OSD in the PG has persisted anything. So in that case, nothing will happen. So for a second situation, at least one of the OSDs finished step 3. And in that case, the local general replay in that OSD and the peering will recover the PG to a consistent and correct state. So for the last situation, none of the OSDs has finished step 3, and at least one of the OSDs has finished step 1. So in this case, yeah, this is the only potentially problematic situation. So in this case, peering will first synchronize the unstable flag to other OSDs in the PG. Since at least one of the OSD has finished the step 1, so it has just updated the PG log version. So the peering will bring the unstable flag to other OSDs in the PG. That is, every OSD in the PG will have the unstable flag on the written object. So for normal object read and write, if it found an unstable flag in the object metadata, so it will just block the client request and start a recovery to randomly choose one of the OSDs to synchronize its content of the written area to other copies. So that is to say, before we read and write the problematic object, it will first synchronize the content to be consistent, but not necessarily correct. That is maybe some old data fixed with some new data, but this is just the block device. It's semantics. When I interrupt the to the right happens. So also for during scrub, we can also make a minimal revision to scrub. So during scrub, it will also check the flag in the object, and if found an unstable flag, it will do the similar process and to synchronize the content within the content of the object within the PG and do the recovery. So this is the second algorithm. For this algorithm, it's lead to some extent big revisions to the current the transaction the object store framework. But the algorithm itself, I think, is good and is elegant. But in terms of the implementation, yeah, it's some kind of harder. So yeah. So that's basically the description of our blueprint. So what's your option or your suggestions?
So I would like to point out that the bad case is the data center failure case, and it does happen.
Yeah, yeah.
And
So
moreover, it's probable that you would have writes on a single object that all end up in the unstable case.
Yeah.
In that case.
Yeah. So yeah, for the first algorithm, it may leave the content of object inconsistent, and nobody except the deep scrub can find that.
No, you'd actually lose the original data. Deep scrub would not be able to restore a consistent state in that case.
Deep scrub will scan the object.
It will restore a state that is the same across all three replicas, but it is not the same as a state that is either before or after the write that was interrupted. It will be in between. It could be torn.
Oh, okay. So it may lead to nobody can find this inconsistency. So, but that's really matter? They just
yes.
Also my question. But does really matter for the RBD situation? So it may happen that for two consecutive read, it may read out different content, right? But it's still like the old data mixed with the new data, but it's different. So this is area, this is behavior. Is the client acceptable or not? That's just my question. Yeah, I think
generally,
if we turn
really
the readability on, the read may fall into the slaves, right? So yeah, so if the first read hit on the master object and the second read hit on the one of the slave object, and the contents are different, so the two consecutive read will.
No, it doesn't matter. They could all actually be the same torn write. They could be the same value but torn. That is halfway between the state before the write and after the write. That's the concern.
Yeah.
Because the write you're performing, the reason why X4 has a has an ordered mode is because you can't do atomic writes to a disk. Right.
So yeah, so I think even the X4 could allow this situation to happen, right? So it doesn't general
Yes, it would, which means applications running on top of the ext4 have to be super duper careful about that.
Yeah. I think yeah. Even ext4 on top of us could allow this situation to happen. So how about But the thing is some kind of difference that we leave some of the contents in the copies are different. That may lead to two read will return different content. That sounds kind of weird for the client or not.
I'm sorry.
For the client. I mean, in our case, for the first algorithm, we may leave the situation that the content for the same object, but just in different copies, right? And the content will be different because of a crash. So
so that's the less bad version. We can detect that case on restart. You're correct. The problem is that we might all match, but be in a state that is halfway between the two writes.
Mm-hmm.
So it's not that the OSDs are inconsistent, although that can also happen. But you're correct. The procedure you've outlined here means that they won't be. We'll know that they're possibly inconsistent, and we'll correct them on OSD restart. That's not a big deal. The concern is that without journaling, we have no way of knowing that that either we wrote the whole data or none of it, because we don't have the old copy anymore. In other words, if we had whole object checksumming, we would no longer match the checksum before or after. Which you're right, X4 and various other file systems do allow to happen, but it's a pretty big semantic burden to put on your clients.
It's also a bit of a different layering issue. Like if X4 is used to recovering from local power failure, but if you have a VM running and perhaps part of your Ceph cluster goes down from some power loss on that side, but the virtual machine continues running, and so it has the data it wrote, but then the Ceph cluster comes back up with this torn write, and the file system can get corrupted because it sees inconsistent state. So the X4 doesn't get a chance to actually do the recovery because it has no knowledge that the Ceph cluster, the disk has gone away and had experienced power failure.
Yeah, even if it were running in ordered mode, it would not know to preserve those journal segments and rerun them.
Right.
On the VM side, that is. That's a good point. I haven't thought about that.
Yeah, but if we step a bit backward, if we look at now the HDD, it still has some kind of mix. If we written some data and the failure on part of during the write. So if we assume that RBD and HDD has the same semantic, is that acceptable to accept that we have some mixed data?
Well, it might be if the VM, if we propagated this IO error back to the VM and forced the VM to reboot. That's the problem. Because normally you don't get a torn write without a power failure. So the VM, as Josh was pointing out, you wouldn't just continue on running with a torn write. That would be a faulty disk. That would be a disk that was not performing correctly.
Yeah. So at least for the second algorithm, we can exactly mimics the semantics of this disk. Yeah. Did you say that before? But
yes, except for the fact that users wouldn't be notified that their write didn't succeed. They didn't. I mean, if they were present to replay the write, then we could do that. But they might not be, and the semantics are that either a write happened or it didn't. You're not supposed to get a partial write.
It's possible that we could, like, if the client is still running, then it's acting like an RPD client running in a VM. It could be assuming that it either didn't get a response back until the write was totally committed. The client side would still be resending that operation, and normally the OCs would be rejecting it because it was a duplicate. But we could actually make it record the last unstable transaction and which transaction ID it was, which client it came from, and then actually apply that on replay from the client.
Yeah, we definitely have to do that.
If the client isn't running anymore, then it needs to reboot, and if then the X4 journal has a chance to do the replay.
From my point of view, there are other semantic problems with RADOS. That only really works for item-potent operations, which not all writes are. RBD writes usually are, but you can build librados transactions that aren't. And this would make that problem much worse. And in other words,
it's not general purpose, is what you're saying.
You can make an argument that that's kind of It would be very specific to the RBD use case, because RBD, you're right, is sort of in a weird position where the clients actually don't really expect untorn writes. They just expect that writes that succeed aren't torn. But that's really, really unique to RBD. No one else uses RADOS that way. And this would be a great deal of code. This is actually quite complicated. For one thing, it's our RBD relies on this too. We would need to be able to account for pipelined writes, and that's concerning to me. You'd need to potentially deal with several uncommitted transactions on the same object in order to preserve that performance advantage, which would be subtle. And you'll also run into a thing where the data you write to objects in the file system won't necessarily commit in the order that you submitted it in, which is fine. But it means that if you have 10 journal entries, or 10 log entries, I'm sorry, in the PG log, you may have 1, 2, and 5 commit, but not the other ones. So the peering logic will need to be very careful. On the plus side, it is possible to avoid some of the problems of case 3, because we may be able to roll back that unstable case. If one peer has the unstable flag and the others don't, we know that that's a rollbackable transaction, and there is machinery for that. So that might be interesting. Also, I don't think it's possible for us to see that flag during scrub. I think that you're correct that the second option algorithm makes that not possible.
Right. So yeah, we can revise the scrub to check the object the flag.
No, I'm saying during scrub you would never encounter a situation like this. The second option algorithm, I think, makes it impossible. You will always correctly repair them to a consistent state. Not a correct state, but a consistent one. All you have to do is read the end of the log, as long as you're careful about maintaining metadata persistently on each replica about which inconsistent objects they have, so that the primary knows after the next peering interval that they need to continue recovering those objects, even if the log entries have been trimmed. But that's doable.
Okay, so yeah. So besides this, the RBD is a very important use case for Ceph. Yeah. Actually, we are mainly using RBD. Using RBD in cloud platform, and another use cases, just I mentioned, we can make it an internal use, for Ceph internal use, like the cache tiering and the multi-object transaction support. Yeah, those double generating.
So the cache flushing case I'm not worried about, because you can always delete the object before you do the flush, and that would allow something like NewStore to write it without a double write. So that's trivially solvable.
So But for the okay, so you mean for the cache tiering, there are no like the small overwrite situation? Just
I'm saying it only matters in the small overwrite case. That's the only case that makes where this can happen. It can happen with the transaction case you're about to present, and that is an interesting case because the coordinator OSD must have a persistent record of the in-progress transaction. Yeah. So you're right. That does act as an extra journal.
Yeah.
Still, though, I guess I'm just skeptical about the complexity.
So overall, what do you suggest? Is it doable, and which option do we choose?
Well, the second option adds another. Well, okay. The second option adds another commit latency. Is that okay? What do we get for it? Hang on.
Yeah.
I think the only thing we get for it is that. Oh, actually, no. Hang on. You're right. With case 1, you actually would find inconsistent objects in scrub. Possibly. You'd actually have to, after you completed peering in order to make this work, you'd have to scrub backwards the current PG log all the way to the end, or at least all the way back to last That might not be so bad. Last back to last update or last completed on disk LCOD. Because we keep a record of the most recent log entry that has been persistently committed on all replicas. So you can be sure that everything before that has been persistently committed. So you just need to scrub everything after that.
Yeah.
So you'd have to do that, and you'd have to remember, you'd actually have to do that before accepting or rejecting any client requests. Because if you get a client request for a journal entry that has already happened, you can't reject it until you're sure that the object is consistent. Because if it's, or not reject, but early return with success. Because you may need it if you find out that the object is inconsistent. So it may introduce a bunch of additional latency to hearing, which isn't the best thing. Yeah, mostly it's just that the OSD is so much simpler to work in if we're sure that operations written to the object store are atomic. It's a really, really helpful abstraction. I suppose we'd have to, in fact, you wouldn't be able to do this in general. You'd have to specifically mark submitted transactions as being data only, or as being metadata journaled only. In fact, you'd have to mark specific write operations as being metadata only.
Yeah. So those have to be done. Yeah, those have to be done, and we need also extract some special operations like clone. Yeah, we made we need to make it do the traditional way. Do the traditional way. The whole bunch of things are thrown into the journal. Yeah, like the clone operations. Yeah, we need to classify those operations, and we may add a flag, a mount flag, or mapping flag to the RBD.
Sure.
Yeah, we can allow the user to explicitly.
What bugs me is that for really small writes, are you sure that it's the double write that's hurting you? Because double writes are usually a problem with big bulk writes, right? The kind that we would probably be able to do a copy on write for. You'll be dominated by latency and the journal write latency itself, not the journal throughput in that case.
So according to our test, we think that for the RBD situation, we observe it's mainly the small overrides. Yeah. So and according to our observation,
I think if you have an SSD journal, the small object overrides will not be the problem, especially if you have HDD backend as your OSD backend.
I think it's not necessarily the bottleneck, but it is doubling the requirement of IOPS that your cluster needs to support the same number of
no, it's not.
things, right?
No. The whole point of putting them in the journal to begin with is that as soon as you have any queue at all for the journal, you're multiplexing a whole crapload of IOs onto the same IOP. The journal is strictly a throughput bottleneck, at least if we've programmed it correctly.
So I think we even have the HDD as a backend to the SSD. Yeah, but if it can tolerate the client can allow the one write, we don't need the double write. Why not do it? This is the,
Well, because the cost is that you have inconsistent writes. So in other words, if it may well be the case that your bottleneck isn't the journal, but your backing disk, in which case this won't help. But this is fairly easy to benchmark, incidentally. This is very hard to do in for real life if we wanted to merge it. But if you want to find out what the performance impact is, it will be pretty simple. All you need to do is go into the journal code where we're serializing the transactions, and don't serialize the data portion of the write.
Yeah, we can do the test, and according to the performance result, we can see how much benefit we can get. Yeah, that's easy. Yeah, we can do some simple things to simulate the result. Yeah.
Hang on. In fact, come to think of it, you don't need to write to the journal at all. All you need to do is where the journal would perform a write, just write a 4K buffer of random data. If you restart the OSD, of course, it's not going to start, but you don't care in this case. So that would be ways that would tell you exactly whether this will help or not.
So yeah, another thought is that we think the crash is really like the small probability thing, right? So the crash and
yeah, but
yeah, only is especially we have peering and we have copies. So yeah, we have a journal, we have the client retransmit. We have so many other powerful things. So we think it's just really happen for those inconsistent things. Inconsistency and happen. Yeah, I think.
So that's all true, but I mean, that's one way to look at it. But another way to look at it is all you have to do to lose power to your data center is lose power to your data center. It actually does happen. However, again, it may turn out not to be all that big a performance difference. You can simulate it by just not writing the journal transactions when it asks to. It's in filejournal.cc.
Yeah, we can do the simulation first and to see how much we can get, how much benefit we can get.
So you're concerned about the case where you're writing to a file on the same disk as the backing disk?
Sorry?
As the journal. The configuration you're worried about is where the journal is a file on the same disk as the backing disk?
Yeah, we are.
Or a partition on the same disk?
Okay, so
if it's an SSD, it's unlikely to matter.
Actually, in our platform, we have only one disk, and we have to put the journal, both the journal and the data partition in one. That will definitely benefit from our design.
So yeah. So I'm going to point out that it's possible that the problem isn't the throughput, but that you are the disk write head is having to jump back and forth between the file system area and whatever was allocated for the journal. In that case, this won't help because you still have to journal something. So you're not getting sequential writes, you're getting 2 random writes. And the size of the second random write doesn't matter so much. It's that you're having to jump to the journal at all. So that may be a problem. The simulation will tell you.
Yeah, I understand. So one of the advantages of journal is make the random write into the sequential writes. Yeah. So.
Yes, which it may not be doing in your case. So.
Okay. Yeah. We can try the simulation first and but at least for our situation, for our one disk situation, that definitely helps.
Well, it might. I'm saying if it's dominated by the seek, it won't help.
Yeah. If it's dominated by the write operations, so the journal could not hold all the writes. Yeah, to make them. So the journal if is not large enough, to hold all the random write into the sequential write.
It's that the file system scheduler is constantly jumping the disk between performing writes on files that you're writing at the same time and the journal. It's not that it's not big enough. It's that the disk has a limited number of places it can write at once.
Okay,
it may not be what you're seeing. The simulation will tell you one way or the other, but yeah.
Yeah, we will publish the simulation result. Right. Yeah, we will first do that.
Yeah, so I have 2 concerns here. One is that even I don't think that will help in your case, but even that this change help in your case, it seems that this is not the general case in common setup. Most of the users will not doing their setup like this. And the second concern is that as a cloud operator, you are doing some kind of consistency trade-off, but from from client perspective, how can they know that? I'm a client and I'm a customer and I'm trying to run a VM on top of your cluster. How can I know that do to do any trade-off on my consistency. Do I still have the strong consistency, or I need to do some tricky way to use your service? I think we need a way to.
Actually, in the first option case, as long as the VM doesn't die, it would actually still provide you strong consistency. It's that if the data center crashes or you lose all 3 OSDs at once and the VM fails to resend again.
Yeah. And also,
Go ahead.
So the inconsistent is transparent to the customer since we are simulating the semantics of a block device. So at least for the second option, we keep the exactly the semantics of disks of the block device.
Well, that's only sort of true.
Right.
For one thing,
so,
if the VM process reboots during that time, it would look like a clean shutdown to it. For one thing. Yeah, it's not really disks some semantics.
Yeah, and we also need to we also lose the if we do that, we cannot share running both object store and the RBD in the same cluster. We lose that ability.
Actually, you could tag the RBD operations as being sloppy, and allow other RGW or whatever to run with normal consistency rules. I think.
Yeah.
I have to think about that, but I'm pretty sure.
Yeah. We can implement just for the RBD granularity. We want to improve. You can mount the system disk of a virtual machine as the metadata-only mode. And
however, if anything else in the same cluster, anything else running in the same pool as these objects would still incur the same costs during peering, the same unavailability period, which is not great.
Oh, so you are saying that the peering cannot distinguish which object belong to the RBD if they are in shared pool.
In case 1, there's no way to tell from the journal entries which ones were sloppy and which ones weren't. I guess there would be if you could look at the transaction. No, but yeah, that would be a lot of complexity. Anyway, it's a thought. I think the first thing to do is to find out whether it would actually help at all.
Yeah. Anyway, we can first do the simulation and see the benefit. How much is there?
Yeah, because the cases where you're writing large objects or large extensive objects, there are strategies we can employ that avoid all of this, that allow us to have the same semantics we've always had, but not do a double write. The case that matters is really small overwrites. And it seems to me that it's possible that in that case, the journaling simply doesn't matter. That the metadata you have to journal is already on a similar order of size. And that buffering the data as well simply doesn't make that much of a difference. Most people complaining about double writes are complaining about double writes for large objects in just RADOS GW, and we have other ways of solving that. So we'll have to see what the testing shows.
Yeah, we can see from the perspective for the RBD, and we will do the test in the virtual machines to see how much we can gain,
Sure.
From this.
Actually, our data on RBD performance is really showing that small overwrite is not another problem. We are consistently can see the HDD can run to 200 IOPS. That is the HDD bottleneck. And the journal, since we use SSD as a journal, so journal is really not the bottleneck. So the problem turns out to be if the optimization only work for certain kind of deployment, should we introduce that kind of complexity into the code?
That's my concern.
I see.
Besides which, we're going to be introducing a bunch of other complexity to handle this in other ways. It's just such a nice abstraction, having all writes be atomic.
Yeah, for other cases, let us think of another extreme case. How about the full SSD situation? So if we have full SSD situation, yeah, we can.
No.
I think. Yeah.
No, in the full SSD case, the problem is that the Ceph code is not fast enough. There's a lot of bottleneck and the locking contention in the OSD code. Nowadays, we even cannot make SSD full utilization. So this is not the problem till now, I think.
Besides which, small overwrites in an SSD invariably mean a certain amount of wear leveling. So there's already going to be write amplification at a lot of layers of the SSD. One little bit extra for our journal probably isn't going to hurt. I may turn out to regret those words. We'll see.
Yeah. Anyway, it depends on the approach. I think. Yeah. If SSD could, it could support. Yeah. And also, yeah, since even the ext4 could allow this to happen. So I think in most cases, the client application could tolerate such error. Anyway.
So we've about exhausted this one, have we?
I think so.
All right.
Yeah, I think so.
Hey, we're not running as far behind now, or ahead.
Right.